All right, let's get going. All right, so this is basically the idea, is that we're interested in being able to say something about how you figure out what exactly is underneath your feet. And there are a variety of ways you can do it. The most common is by drilling and sampling. If you drill and sample, most of the cost in drilling and sampling is for the drilling part, and you're left with a borehole or a well bore. It's often crazy to not utilize that and to put in a well or a piezometer that then can give you information other than the things that you've removed from that. And so the first part of our discussion, I guess, is talking about profiling. Now, don't want to go through everything that's in here, but I'll zoom on a variety of different modes. Yeah. So this is the deal, right? So we looked at, or we tried to look at the Smithville site on Google, and you saw that it was basically a field that sits not in a subdivision, but in a kind of semi-rural area with some houses around. Nothing particularly remarkable about it. Nothing that would give you any clue as to what physically is going on in the subsurface, unless you do something like pincushion it. And so these individual dots within this larger region here are the holes that have been hot because they've hit free product. Not very deep. It's of the order of 10 meters. 10 meters or 30 feet, 30, 40, 50 feet deep. So a very shallow site. And so relatively easy to drill. But if you remember the stratigraphy, you remember that it's clay till, which is a soil, which overlies a couple of limestone aquifers, which are separated by a low permeability layer. Not really a shale, but it's a low permeability limestone aquiclude, or aquiclude, I guess, not aquitard. And so the interest in this is to be able to figure out exactly what is there. And if you're looking at splitting the investigation methods between quote-unquote direct methods and indirect methods. Direct methods, you physically go in and you take a sample. And you can imagine that direct methods could be one-dimensional. You drill a hole. So you have an observation of what's along the length of that. Maybe you take either discrete samples out, or you take continuous core out along the hole, and then you therefore know something about the stratigraphy, right? So when you're standing in the field, you don't know it's 5 meters of clay till, 5 meters of limestone, 5 meters of aquiclude, etc. You just know there's something underneath your feet. So one way to do that is by sampling along a length. You can also sample in 2D. Typically, in 2D, if you sample, you do it with a backhoe. You just cut a slot, a trench. Sometimes you might go down in the bucket of the backhoe to see what's there if you're feeling lucky. That's a kind of a dangerous thing to do. It's probably not. It's probably illegal to do that, but it's sometimes done. And if you want to look at the three-dimensional picture, short of being able to excavate everything in which you've destructively destroyed your site, you can't do it unless you use geophysics. And so there's this kind of interaction between maybe drilling a hole, maybe doing some geophysics to correlate what you see in that hole across the rest of the site, and then depending on what you find in the geophysics, maybe drilling some other holes in other places that give you confirmation of some things that you really want to see. So you might be looking for NAPLs. You might see it in the geophysics, although it's not very easy to see. Some things like GPR and electrical methods can work. And then once you find out with the geophysics, maybe you put a hole down to confirm whether it's there or not. But the first thing we'll talk about is direct investigation. Trenching is pretty straightforward. You rent a backhoe, $75 an hour. They dig a slot. You get to see what's in place. It's kind of destructive. You don't get a useful borehole out of it, but it's used. If you want to drill, you might be renting a rig. You might be working as a logging stuff that comes out on a rig. And so they come in, I guess, two end-member varieties. And those end-member varieties, which we'll talk about, are for soil and for rock, with the in-between variety being kind of for both of them. And so we'll talk about these three varieties when we talk about drilling. And they are augering, where you can take a corkscrew and basically screw it into the ground. The stuff that comes up on the auger flights is the soil that's there that has been transported from depth. You log it, you put it in a bag, and you say by classification what is present at depth. Or you can do more sophisticated things using hollow stem augers, which allow you to be able to actually get down to depth and physically retrieve an undisturbed sample, which you then bag and send back elsewhere. So that's one end member where you can actually go down and take samples at discrete locations, continuous if you do it all the time, that tell you something about what is in place. If you're in rock, obviously you can't just screw this thing into the ground, and you have to use diamond coring. And so diamond coring is something which is basically a cookie cutter, but it's on a very long string, and that cookie cutter, as it rotates, it abrades the material at the tip of the shoe, and it allows this cookie, the core, to go up inside the core barrel, and then you can either pull the drill string and take it to the surface, or you can actually retrieve it by a wire line with the drill string still in place that keeps the rest of the hole open. So both of those end members, soil and hollow stem augers, rock and rock coring, give you full samples, so you'll be able to see the stratigraphy as you go down. It doesn't really tell you anything about the material properties of that, permeabilities, porosities or anything, but you can do some of that stuff in the lab. And also you can put, in the remnant holes, you can put piezometers that allow you to do well tests to, say, measure permeabilities. So those are the two end member behaviors where you actually get a sample. The intermediate case, which can work both in soil and rock, is by using tricone drilling. It's what they use when you drill water wells in this part of the country. It takes no core, it just destroys everything in front of it and sends rock chips up in the drilling fluid. Drilling fluid can either be water or drilling mud with bentonite in it to give it some weight, or barite to give it some weight, or it can be air with a foam in it to be able to carry the materials up to the top. And as a result of that, you end up with a hole, but the only samples you end up with are drill chips, which might be, well, they're probably rice size that has come out. And so you can tell something about the material that's down there, piece of sandstone, piece of limestone, but you can't tell anything about its structure in terms of what the fractures might look like. So you end up with an empty hole, some samples of cuttings, and so this is the standard method for drilling oil wells. You take cuttings, and then once you have the oil well or gas well in place, then you do borehole geophysics. So you drop a sonde down it. The sonde might be a video camera that you pull along the core hole. It might be a gamma ray detector that tells you something about whether you have shales or clays there or not. It might be a neutron detector that tells you something about the moisture contents of the material. It might tell you what the seismic acoustic velocities are. All of these things you can rent very nicely from Schlumberger or Baker Hughes, and they'll charge you for the pleasure of doing that. And actually, it's not used so much in the water environment business, but it certainly is a standard way of being able to log holes in the oil patch. And so those are the three methods. And so what I will do is I will use some perhaps better figures than those hand-drawn figures to try and make the cases for what those different methods are, and we'll try and look at some different tools. I'm never quite sure what is best to do first. Let's talk about augers and just look at the pictures per se of what these look like. So this is the basic idea. So these cable tools aren't used. Cable tools is the way you drill the Drake well. You have a big heavy weight, you drop it, lift it, drop it, lift it, drop it, and then you bail out the sludge that you create here, and slowly you get deeper. I think we're a little bit beyond that now. Augering is where you drive this screw into the ground. As you screw it up on the flights come the material from the bottom, and you sample it in the flights. And with a rotary hole, you drive drilling fluid down the center of your drill stem. You have these bits at the bottom which just rotate They don't actually abrade the bottom, but you push on it, and so the individual button cutters that exist on this pop off little buttons of rock that then get entrained as chips that come out on the outside annulus of the drill string, between the drill string and the borehole wall, and you collect them up front, up at the top rather. And so if you look about how these things work in soils, I can probably make this even bigger. Can you see this stuff? It gets a bit... yeah. This is just this flight auger. So it's a solid stem that has flights around it. It's screwed into the ground. It has a cutting shoe. And as it's screwed into the ground, it doesn't advance like you screw a nail into or a corkscrew into a cork bottle or a nail into a counter. It actually slips as it goes down. And as it slips, it pushes the material up to the top and you gather it. When you want to take a sample, you have to pull the auger string. So it might just be a 5-foot section, or it might be 50-foot, it might be 10 5-foot sections that you have to pull. And then you can put some kind of sampling tool down into the hole. This is a split spoon. You bang it into the ground. It takes a cookie cutter. You twist it, you pull it up, break open the sampler, and sample the material and take it back to the lab, and then repeat as needed. And so now once you're down at this level, you want to go down another 5 feet, so you put the auger back in the hole and you keep on merrily going down another 5 feet. Once you're down at 5 feet, you pull it and then you do the sampling. So it's kind of a laborious process. The negative thing about this is that things like clays are quite stiff and they'll stand open and keep the hole open themselves. But materials that are quite heavily laden with water and not very cohesive, like sands or silts, will tend to wash into the hole once you pull out the auger stem. And if you do that, then the possibility exists, I guess I could use this, couldn't I? The possibility exists for this material that previously existed on the side of this just to slough into the hole. And so now, when you sample through this, the top part of your sample in here, you might think it's a different level, a different bed at this level, because you've washed all this crud into here. So the problem with using a solid stem auger is that you stand the chance of when you withdraw the string, the auger string, then something collapses and you have to interpret exactly what this means. And you might give a wrong interpretation as a result of that. Likewise, if you're using, so augering, rotary drilling, the two end spectrums, soil, rock. In between these, tricone drilling or rotary drilling is something that will go through soil and soils and rocks. But basically the same idea. You're driving down through here. You typically fill the hole with water, with drilling mud in it. The idea of that is to actually allow this to push a pressure against the wall so the wall doesn't collapse. But then, since you can't take a sample through the tip of this, typically, you pull the string and then you put your sampler in and you have the same problems as before, that you might get some collapse if it's not being held open very well. You can minimize that collapse by using water with a heavier loading of mud in it to be able to push back on the walls, and so you don't get collapse. But the same idea is that you can only get samples by introducing a sampler after you've pulled out the drill string. And of course, a sampler that you bang in to take a sample like a cookie cutter is only going to work in something that's a soil. It won't work in rock. And so in rocks, when you're using rotary drilling, you don't have the option to be able to sample from them. All you'll get are the chips that come out from the top. Whoops, I guess from here, right? You'll get the chips that come out from the top from doing this, because you don't have the option to be able to sample it as you go down. What you do have the option to do is once you pull the drill string is you could run a bowhole camera down and you could look at whatever's there. And so I guess this is making the same case as before. If for some reason your hole collapses, then you end up with this stuff at the bottom and you end up with this sample. The top of your sample is no longer pristine and you're not sure whether, is there really a stratigraphic discontinuity of this place that you should know about, or is it just the muck that came down from here that washed into that? And so those are the methods that end up being used for drilling. Well, I guess I've gone past them, right? So I've zoomed in on this so much that it's made it not so obvious. Okay. So remember, end members. Augering for soil, rotary drilling for rock and soil, diamond drilling for rock only. You don't get a sample with this. You don't get a sample with this without pulling the drill string, but there are hybrid methods of these. The hybrid methods would be something like a hollow stem auger. And a hollow stem auger is this. And so this is now the auger that you drive into the ground is this whole assembly. It has a little U-shaped cutting shoe at the bottom and cutting teeth at the bottom. These are the auger flights as you go up here that allow you to screw it into the ground. But instead of just being a single solid stem with these flights welded on the outside, it's actually a hollow tube. And in this hollow tube, there's a central solid stem that goes all the way down to the tip, and that this little plug or cutting shoe is attached to. So you screw it into the ground. You get down to some depth where you're interested in taking a sample, and then you retract this central section, but you still have the casing basically holding the hole open. And so there must be a picture of this. Yeah, so this is the idea. So you drill down to depth. This is the cutting shoe that goes down to the bottom. This is the solid stem that links it to the top. Once you get down to the depth where you want to be, then you retract this whole assembly, which is this part here, including this, and you leave it open. You put the tool down through the bottom. Now nothing can fall in from the sides, and you actually get a sample which is relatively pristine. Two benefits, right? You're guaranteed that the sample you here have is pristine because this can't fall down. And secondly, you haven't had to pull all your drill string to be able to pull it. It's pretty easy to actually pull these pieces of A-rod, which are 5 feet sections also, and you just pull them out the hole. It's relatively straightforward. So hollow stem augering is one way to be able to avoid that. So augering for soil, solid stem or hollow stem, you keep the hole open in one, in the other you don't, then you have to retract. Rotary drilling, soil and rock, you get no samples really. Have to take the drill string to take soil samples, and in rock you don't get any samples at all. And then in pure rock we do rotary drilling, and rotary drilling allows you to take this continuous sample as you drill through it. And so the idea is basically shown here. So you have a long tube, 5-foot sections, 10-foot sections, 20-foot sections, whatever they are, and the tube is hollow. At the tip of the tube it has a cutting shoe, which is studded in diamonds, which are these portions here. It's a torus, obviously, it's like a donut. And you just rotate it, and it slowly abrades this material. It doesn't chip it off, it abrades it, and slowly works its way down further and further. And as it does, this stub of rock advances up into the core barrel, and once you're down at the full depth of the core barrel, whatever that is, a 5-foot length, often 10-foot length sometimes, 20-foot length sometimes, then it's probably so broken that it's broken off in there. You don't have to twist it to break it off. Then you can do two things. You can either pull this whole assembly out that includes this core, which is present within here. Or if you have a more sophisticated core barrel, which is like this with an inner tube, you can, instead of pulling out this external assembly, you leave this in place and you just pull out the portion which is the internal core barrel. So you have a core barrel inside a core barrel. So this is a core barrel. This whole assembly, including the piece of core that's in here, gets physically extracted through here. You can't see how it goes through here in this particular case, but it gets pulled up 10 feet, 100 feet, 1,000 feet, whatever depth you are. And so you just pull out this core barrel. You haven't pulled out your whole drill string. It's much faster. You take the core out of the core barrel. You put a new barrel on there. Actually, you take the core barrel out. You put a new barrel on the wire line and drop it down. And so while you're taking the core out of the second core barrel that's on the top, you can start drilling again. And so these come in a variety of different flavors. They're single or double or triple barrel core barrels. So this is a single barrel core barrel. You have to take the whole assembly out to get it up to the surface. A double barrel has the core barrel inside here that might rotate as the thing goes around, which is not so good as a triple barrel core barrel, which has the core barrel that stays static on the core as the outer part of the drill thing moves around. and so it means that you don't mash your core up quite so badly. And so those are the main methods of drilling. Their listing of the advantages and disadvantages of all the methods, I think we've kind of said them. I was going to use iPhoto to be able to do that. Let's see so let's look at some pictures if we can get them. I don't know why iPhoto crashed before. I don't want to see family pictures, do you? Technical photos. So, okay. I'm not sure. Well, let's just look around these. Yeah, not necessarily. Oh, these are probably not bad. Drill rigs. Let's see if I think if I make this, they go for. So these were taken on a pretty low resolution camera. So now what happens with iPhoto with this high resolution screens is it? So this is a drill rig. It happens to be a drill rig that's set up in the Caribbean, next to Antigua, the island of Montserrat. This is the drilling boom. This is the drill steel. This is a rotary coring rig, like the rotary rigs that we talked about. My kids when they're young. Ash clouds from a volcano. Water for the drilling truck. They're not all together. So this is the core that comes out of this is typically, so this is for dimensions, this is 3 inches across, 4 foot maybe length, 3 foot length of the box. And these are just the individual strings that come up. Sometimes it comes up broken up. Sometimes it comes up with natural fractures and doesn't get badly fractured. You can never quite tell whether it's fractured like this in place or whether this is all drilling damage that has happened because you haven't drilled it very well. And you can imagine that's probably an important thing to know if you want to say something about what's going on the subsurface. Is that coming out long there, or is this downstairs? So, drill rigs. So this is a turntable. This is the drill steel going into the ground with a connection on it to be able to pump water down the drill string. This whole thing turns around, and as it spins, it slowly moves this head down to push it into the ground to actually make it abrade more. Once it gets to the bottom of the run, you uncouple this hose, you pull another piece of drill steel up into the mast, which is what that boom is for. You screw it down onto the one that's before it, and then you attach the fluid injection part that circulates water into it to the top, and then you just keep on drilling. This happens to be a wireline rig. So yeah, you can see the same assembly here. This is going into some casing, which just keeps the hole open. There's water coming out. Actually, probably not much water coming out from this casing. This is a hole with lost water that didn't, which is bad because your bit gets hot and gets stuck in the hole if you lose water. But this is partly on its travel down to the bottom. I'm going to have to make all of these large. Yeah, so this is the casing, and this is just the drill string. This is a drill bit, and so this is the drill tube that goes up one section. These are flutes that allow the water that gets washed down inside this drill tube to come out and go back as return fluid. So it comes down the center of this. It would have a core barrel inside this. The water would come out here. These diamonds would be abrading on the bottom of the hole, and the return fluid would be washing up, not chips, but basically flour, up to the back, up to the surface. And there are diamonds, you can't really see them, there are diamonds on the front part of this, and there are little diamonds, these little bumps are all industrial diamonds, which are making sure, of course, that the hole you drill is larger than the drill steel that follows, because you don't want the drill steel to get jammed in the hole. So the reasons that these sit proud is to be able to do that. You see here as well, this, you can't see it actually here, but this little reamer is a row of industrial diamonds as well that also over-reams the hole, so that you make sure that you don't end up with your drill steel actually stuck inside there. When you want to take a sample, then what you do is you drag a wire line. So this is the wire line. So I'm trying to think, this is a few inches across, this is probably 10 feet long. This wire line goes in the bottom of the hole, and the tip of the wire line would be right at the front of the shoe and would go up into that last piece of casing. This is the outside diameter of this is basically very slightly smaller than the inside diameter of the drilling shoe. And as you advance, the core moves up inside this material, and then when you want to retrieve it, what you do is you send down this fishing tool. So this fishing tool goes down 100 feet down to the bottom. You can kind of see that these are little spring-loaded clips on the side, and the core holder has a little conical clip on the top that has an undercut, and this just clocks on this and the ratchet catches it. The ratchet catches it, it releases the thing from the drilling cutting shoe, and then it physically, on a piece of steel cable, it carries this all the way up to the bottom, the top of the hole. So this is the fishing tool that takes the wire line. That's casing. That's so this is the tip of the core barrel. The water would come down and out of these holes. This is, I guess, this is the assemblage at the top. Yeah, maybe you can see this. Right? So this is the core barrel. As you go down to the bottom of this, it's the open end that is at the mouth at the bottom of the hole. And so this is going up to the top of the hole. This is all gimbaled, so it's linked. This little thing here that you see bent over would actually be sitting up. And so this little conical thing is the thing that the fishing tool latches onto. It grabs onto it, and it physically pulls the whole assemblage up through the top of the hole. Yeah, you can see it here. So this is one. So the fishing tool latches onto this and pulls it out. So obviously in doing that, you're able to get the core. If you're down 200 feet and you have 10 sections, you don't have to pull 20 10-foot sections of pipe, unscrewing them each time, linking on, pulling another one, grabbing it, unscrewing it, taking it off, etc., and then doing the same to get back to where you are. Instead, you just go down to the bottom of the hole and you take your sample out. And they're the kinds of samples that we just looked in there. Yeah, so you see that again. That's the fishing tool. That's the attachment on the wire line. You'll notice also, as I mentioned, there are two wire lines. One's down the hole. It's catching core. When you pull it out, you keep it out, you put a new one on, and while the other one is now drilling, you can spend your time hitting this with a hammer. Whoops. Hitting this with a hammer sometimes to actually get the core to come out, depending on how it's jammed. It doesn't open up in any way. So what else do we have? Drilling mud. You want water to be able to lubricate the bit. I'm not sure this says anything other than what you already know. Drilling turntable, maybe you can see a bit better the fact that this is the connection for the water line going in here. Water goes down inside the drill string down to the cutting shoe, comes out the cutting shoe, and back circulates around the, in this case, the casing, which describes the hole. Tilt meters, not relevant to this, but sometimes when you do fracking jobs, Pintech have made a business out of trying to figure out where the frack goes by drilling little holes, maybe 5 feet deep, putting in these holes tilt meters, of which these are tilt meters, backfilling them with sand, fracking them. They get, as you frack, the ground distorts, even if it's 3 kilometers down below you, and you can triangulate from the deformation that you get on these particular tilt meters exactly what's going on underground. This was actually to be installed on a volcano, but same idea. You can look at deformations and you can say what's going on in the subsurface. So Now this, not, oh yes, so the drilling boom, I guess. This drill rig all fits on a cart that can be driven down the road. This was actually transported to the Caribbean in a 20-foot shipping containers, things you see on trains going across the country. Other random things. So what else? Is there anything else? Well, maybe you do see some stuff. Yeah, well, 2 drillers drilling. Night drilling, work 24 hours on this particular job. I'm not sure there's anything else to see on this. So multiple shifts of people logging the core. It's actually next to an active volcano, which is kind of interesting. But okay, we won't talk about that yet because we haven't really talked about that. What other methods? Do we look at these? I guess I should probably have looked at this, right? This is a core shack in Sweden, actually at the Swedish, one of the candidate sites for radioactive waste in Sweden. Maybe I can make it full screen. Maybe. This is a core shack where you have the drill all laid out. Very formalized process of being able to inventory this, and someone logs this. So this is clearly core drilling. I guess we're back in Montserrat. That was so. This is our idea of a drilling tank. It wasn't a very smart idea. It was one of the local inhabitants enjoying it. So the problem is you need water to be able to do this, and you might not be close to somewhere that has water. And it turns out, maybe we'll see it again, there was a broken down tanker. There were 2 water tankers on the island in this particular case. And so it was almost impossible to get water. This is a drill site outside Boston, on the outskirts of Boston, in clay, with a drill hole down. This is a rotary and augering rig, I guess. This is a piece of casing that wasn't really to do a standard job. It was actually to test out a probe which was going to be used in the Gulf of Mexico to try and measure pore pressures ahead of the open hole. Doesn't matter here for this. But this is a typical drilling rig. Comes on with a truck, driven to the site. This is the business end of the drill steel that's used. This is a monkey hammer to drive these sampling tools into the ground. It's set up under an overpass in this particular case, on top of the hole. And the process is basically this. So you put in casing, you drill, you over drill the hole with a larger drill diameter. You put in casing to keep it open close to the surface, and then you use a smaller drill steel to drill down through that and keep on going with a rotary drill. Now that you have the casing, you see that this is just a a 3-part plumbing fitting that you might have on a septic system. Right? It has a tube that goes up and a T that comes off the side, and all this is doing is that the fluid which is going down inside the drill string. This is the fluid going into the drill string, down inside the drill steel, out at the tricone at the bottom, and then recirculates back up into the casing at the top, and then gets collected back in this recirculation bath, and then goes back and is re-injected. And so that's basically the process. You don't want to keep on reusing new water all the time because you may have added some quite expensive mud or weighting medium to that, so it works better. And so yeah, you see. So this is the drill, steel goes down. This is the water going in for the drilling fluid. This is a gimbal that allows it to turn like a universal joint, and it just drills down into the ground. Putting a wrench on it to break open steel. So if you want to add more components on it, you can do that. Set up on hole. All the fittings, of course, are tapered, and so they don't lock. And so this tapered male fitting goes into a similarly tapered female fitting, and so they always you never drill counterclockwise for obvious reasons, right? You just unscrew all your drill string in the hole, and so you always drill forward. Even when you're retracting it, you're drilling it in the same direction. And so these rigs typically come equipped not only with rotary, this is a rotary rig that doesn't take samples, but it also serves the same purpose as an auger rig. So these are solid stem augers. Actually, they're hollow stem augers, I think. Yeah, these are hollow stem augers. So this is the hollow, this is the flights on the outside. No, I think they're solid stem augers. So this is a male joint goes into this, and then a pin goes across that. The reason I think it's solid stem is because, of course, if you have a pin that goes across this, you can't have something that goes down through that pin to take out the central part. And so these are a series of solid stem augers on the side. This is a tricone bit. Can we make that larger, maybe? So this is in this case, this is the rotary bit at the bottom. Goes down to the hole and has these cones on it. It's not powered. It just rotates on the bottom, and these button cutters cut off chips, break off chips that get sent to the surface. And we haven't talked about any sampling methods. So let's see if there's anything else that we should talk about. Yeah, okay. Maybe we should go back to this. So we didn't talk about sampling, but we could talk about sampling. Let's do this. So we made the point that once you go down below ground, if you have a solid flight auger, hollow stem auger, or a rotary drill, in all cases you don't get samples unless you pull the drill string or put a tool down there to do it. And so in soils, the different tools fall into two categories. If it's in gravels or sands, then it's usually called a split barrel or a thick wall sampler. And the idea is that it's just a tube. It's a relatively thick gauge tube, maybe 1/4 of an inch thick wall. It has a cutting shoe on the bottom, and you lower it down the hole on drills, A-rod, and then once it's down at the bottom, you physically bang it into the ground, and you bang it into the ground by using a monkey hammer, this hammer here. So it's a big heavy weighted tube with a central stalk on it. The stalk goes into the top of the drill, the A tube. You lift the heavy weight up with a capstan on the side of the rig, which is over here, and then you just let it drop. Bang, 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 and it knocks the core tube ahead of the bottom of the hole, and a sample kind of gets washed up inside, and you want then to be able to take that sample up to the top just by twisting it off at the bottom and physically pulling it out. It has a valve here, so that if you get water in the A-rod, when you pull it up, the water doesn't just physically flush your sample, which would be kind of a waste. And so coarse materials like gravels and sands, you'll physically have a thick wall sampler, you'll bang into it, get it onto the surface, you break it in half by taking the shoe off, taking the back end off, and the middle parts between those are just two halves of a cylinder that open up that allow you to take your sample out. And so that's kind of the generic sampling type for coarse sands. Things that don't have cohesion. Things that do have cohesion, like silts and clays, you can get away with using what's referred to as a thin tube sampler. And so the idea for this is it's basically a cookie cutter. So it may be 1/8 of an inch or 1/16 of an inch thick. It goes onto an assembly, but it has a really sharp cutting shoe on it. You can cut yourself on it, slice your finger on it. It's pushed down to the bottom of the hole just like any of these other samplers, but instead of physically being banged into the ground, it's just physically pushed into the ground and then twisted to break off the base of it. And then you hope again when you pull it out that you don't physically wash off your sample when you go down. And so these come in a variety of kinds. They come as just regular Shelby tubes, thin wall samplers. So the main difference is the thin wall means you get a sample that's not very disturbed, so you could perhaps take it to the lab and measure permeability on it. A thick wall sampler is has a thick wall, and so by pushing it into the ground and banging it into the ground, the sample inside it gets disturbed. It's not really pristine anymore, and so you can't really use that to take to the lab and do permeability, but you can use it for gradation and stuff. So that's the primary difference between these. The other variation on this is the idea of a piston sampler. So the idea of a piston sampler is that you have a thin tube, just like a Shelby tube on the outside here, but when you push it down the hole, you advance a syringe piston down to the bottom that doesn't leave an air gap here. It gets down to the bottom of the hole, and now when you push it in and retract this thing at the same time, so that this piston allows the sample to go into the Shelby tube, or the thin wall tube. But then once the sample is in there, you can pull on this piston to put a vacuum behind it, so you actually hold the sample in here. So if you're doing with clays, which are nice and sticky, you can do it with this, and you just pull it out, and you still get a sample. If you're doing it with silts, which are not so sticky, if you try sampling it just with one of these, as soon as you pull it out, it'll just slop in the hole, and you won't get anything out of it. So piston samplers allow you to do that. So the two main kinds. Soils, such as sands and gravels, thick wall cylinder. Soils, such as silts and clays, use a thin wall cylinder. Undisturbed samples, useful in the lab. Highly disturbed samples, less useful. And of course you can use core diamond drilling in these things as well. And so did we have some pictures of these? What do we have? So this is exactly that. So this is that piston sampler. So this is the piston. This collar is where this very thin-walled Shelby tube will go. And these little lugs here are screws that you screw in so you can get the sampler on it. You arrange it so the holes in the sampler are on top of them, and then you screw them back out with Allen keys to be able to lock the sampler on. And then when it's ready to go down, this bronze thing is the Shelby tube, the sampler. This is the end of the piston. Get it down to the bottom of the hole and then retract the whole thing together. That's people deliberating over the piston. That's the piston. That's the assembly. That's a sample that's come up. So this now is a tube. There's 18 inches probably of sample in this at the top. This is the retracted piston. Nice clean end at the bottom of this. You can do some experiments with it. You can twist a Torr vane in it to be able to measure the strength, which allows you to classify the clay, for instance. And once you have the sample, a typical way of sealing it is to cut some of the clay off. So you have a bit of freeboard, melt some wax with a tiger torch. This is molten wax, and then pour it into the top of the tube and seal the moisture in, and take the undisturbed sample back to the lab to do whatever you need to do with. These are the holes that go onto this assemblage. So put some end caps on it, put some labels on it, and you see what this is. So this is just the process. Measuring the strength at the end. Torr vane is just, you twist it, it's like a torque wrench with some little feet in it that go into the clay sample. When you twist it with enough torque, those feet will fail and turn, and you know that you've failed it. Yeah, leave these little feet. So quite rudimentary, but does a job. These rigs are used in the UK. This happens to be in China. I think it's in where is it? It's Jinan, which is Shandong province, I think. And so this is the same idea. Stilts. This is actually a cable that goes down that you beat into the ground. Still used in the UK as well, or used to be. And you clear out a hole, and then you take samples from it. And we haven't talked about that yet. Maybe look at it. See, I think it's.
That's the movie again.
Yeah. This is when I use the camera, but not in movie mode. Yeah, there were some early pictures, I guess, up here. What else do I want to talk about? Yeah, we'll come back to that. The other way to do site investigation. So we've talked a little bit about augering. We've talked about rotary drilling in this one. So augering and rotary drilling in these ones. The other way to be able to profile is to be able to do something called continuous profiling. Quite popular these days in the environmental area, and it involves pushing basically a tapered probe into the ground, and you push it into the ground. It's 10 centimeters cross-sectional area, so it's about 1.5 inches in diameter. You push it into the ground at 2 centimeters a second, basically 1 inch a second, and you measure the force that you apply to it to be able to push it into the ground, both at the tip, the end bearing, and the friction that you have along the sides, and also you measure the pore pressure. And so what you get are a whole bunch of profiles of how the force at the tip changes as you push it into the ground, how the friction along the side of the tip assembly changes as you push it into the ground, and also the magnitude of the fluid pressures that you generate as you push it into the ground. And so then what you can use is you can take these magnitudes of these values of these three variables, so tip resistance, friction or force or ratio, and pore pressure at any one depth, and you can use empirical charts to take your knowledge of the cone bearing you had, your knowledge of the friction coefficient you had at that depth, to say what you think the kind of soil is from this value, just empirically determined. In this particular case, it says that that is sandy silt to clay silt. So you know something about the materials. And you can also, if you take magnitudes of pore pressures, you can use those pore pressures to directly figure out what the profile of permeability is in these soils only as you go into the subsurface. So that's become quite a popular way of doing site investigation. And those are the next figures. This happens to be a site in, do you have any Turks here? Izmir or Izmit. Two places. Very similar names. One is on the Aegean coast of Turkey. The other one is on the fault that goes across Turkey, which had an earthquake maybe a decade ago now that killed 30,000 people by buildings having the soil underneath them liquefying. And so this is the latter of those, Izmir or Izmit, at a particular site where they're doing profiling using this continuous profiler. On the North Anatolian Fault is the name of the fault. And the idea is to see what the material is in terms of strength and porosity and permeability, and also principally its susceptibility to liquefy and become liquid, and therefore not support foundations during an earthquake. And so the piece of equipment is this. This is kind of two rams that grab onto a piece of this cone and physically push it into the ground at 2 centimeters a second. And while it's doing that, you screw the next 3-foot section onto it. And so that when you're down at the full stroke of the ram, it releases, goes back to the top very quickly, grabs onto this second piece of pipe and starts doing 2 centimeters a second while you frantically put another piece of drill string on it. And so what they're doing here is the drill string is hollow, but the tip, all the instrumentation at the tip has to come up through a wire, this green wire, up to the logging box on the surface. So you pre-loop the cable through all of these pieces of drill string so that you add them on the cable and the cable comes out of the top of it. So the tip of this, you'd be surprised and maybe, I don't know if you're happy to know or not, but the tip of this is basically a cone which has an element which measures pore pressures here. There's a pressure load cell that measures the force that's applied on this segment of the steel here, and a different one which measures the force on the tip. So in other words, there's a load cell here which measures the force on the tip. There's a load cell here, which measures the force on the sleeve friction. And from those different magnitudes and the pore pressure, you can say something about it. So to start it in the ground, you want this porous frit to be saturated. And so what you do is you boil these porous frits overnight to get the air out of the water. You cover them in silica gel, and then you cover them with a condom in this particular case. So you might recognize the fact that this sheathing is actually just a regular, I guess it's a regular condom in terms of size. And then you physically put it into the ground, and then you just keep on pushing it. And it rips, of course it destroys the condom, and it just then starts taking measurements. So these are probably aborted. This is me taking pictures of my feet. But this is, here you see it. So this is the deal. This is the tip. It's ready to be put into the rig. These are pieces of the drill steel here, but it's easier just to keep it on the ground. It's had the stuff threaded through there. It's ready to go. It's physically put onto the ground, and then this mandrel clamps onto it and just slowly forces it down. Yeah, so you see. And so once it's down there, and then once it's gone down to the bottom of its travel, you then, well, before it's gone down to the bottom of the travel, you put another length on here, and so that then you just release, when this is down here, you release it, go back to the top very quickly, grab on, and basically do a continuous profile. I thought that was, yes, it's Korea, don't know, this is an underground research lab in Korea, one in Japan. Yeah, perhaps we'll see some. So this is just the mandrel. Whoops. Here it's pushing down. This is the rod that's being pushed down. As it goes down, it gets to the base. At some level, you can put another rod on the top just by threading it over the top. And this is a guide that's allowed to go into the ground. And so maybe you can do site investigations with these down 50 or 100 feet depth. You don't need a drill operator to do this. You can buy these rigs. I don't know what they cost. I imagine they cost $50,000, $100,000. But you can rent them and you can run them yourselves as opposed to a drill rig. So they have some benefits in that. Yeah, okay. And so this is the same. Yeah. So this is another form of those rigs. Actually, it's probably easier just to look. This is somewhere in Delaware. Yeah, see. Sitting on a rig. So yeah, these are the frits that they're in silica oil, silicone oil. So they are saturated, so you don't get strange readings. This is the probe with the cable going on to the next one. This happens to be one that actually is called Viz CPT. So the idea here is it has behind it, maybe half a meter behind the tip, it has a little window in it which has a sapphire screen on it, just like the face of a watch if you wear a watch, and a little LED light that looks at the soil that goes past the window. So here they're much more sophisticated. They're not using a condom, they're using a piece of bicycle inner tube to seal it in. Same idea, it goes into the ground. This is the tip, this is the sleeve friction, this is the tip resistance. Right here there's a little peephole with a CCD video camera in it, right here. So this records a picture of the profile as you go down, so you can get some idea of grain size and things. This happens to be University of Michigan rig. I don't know if it's still operating. This is Roman Ritsu, a colleague of mine who works at Michigan. And this is the deal. So this is being pushed into the ground. This is where the camera view comes out. If you can see, not a very good picture. The rig is just raised up on components, making a hole for the probe to go into first. The camera that looks kind of rudimentary, but the camera that takes a video of this. Yeah, so there's a little video camera in here and a couple of LEDs which illuminate the scene, and then the cover on this is basically a sapphire cover, which is the same as a watch cover. Hanging out, hard at work. It's at a petro refinery in Delaware somewhere. And we've got some maybe the videos aren't here. This. What's going on. So this is just putting the electronic coupling, that's the video stream, that's the business end of this with the split that is sealed by
Did you get it?
Yeah, I got it.
That's all stand up. He's getting so all stand up.
This was where I really lost.
Yeah.
This is wild. So this is pretty
It's a jump over.
This is a trampoline. So this is interesting. So this that's yeah. Got out by the skin of our teeth. That's good.
Coming out over there.
Sand boilers.
Got a sand boil?
Really?
So that's kind of where. So this is. Yeah, what is that? Any idea? So they dredged the Delaware. They dumped the stuff into the slurry into these holding pans behind berms, you know, the size of a field, maybe 10 feet deep, and they let it consolidate. Water comes out of it as it kind of compacts, and it gets this desiccated skin on top of it, and actually is reasonably coherent. So we're going to drill in one of these, or use this probe in one of these. So I drove my Jeep onto this surface, so you could walk on it. Certainly, it's absolutely solid. And we parked the Jeep there, and we said, yes, let's do the probing here. So we brought the probe along, parked the probe on the berm, and then drove it down onto this thing. And so the probe is on this Ford F-250, F-350 truck. So it's got a boom, 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 right this thing. And so it liquefies it. And so this stuff is all water saturated. It's quite solid while it's happy. It's just like the Marina District of San Francisco in the Loma Prieta earthquake. It's kind of strong, this material. You shake it with an earthquake, it collapses. It collapses, the water doesn't change volume, and so all the load now is carried by the water. And so what it was that the surface remained kind of intact. The stuff at depth, because of being shaken just by this rig, my car was parked there, it was just sitting down there, it liquefied. So now, unfortunately, the top.
Did you get it?
Yeah, I got it.
Dry and desiccated.
That's all stand up. He's getting so all stand up.
Someone jumped in the rig and drove that off, and I drove my car off as well. But this is it. So I'd imagine it's probably tied together with grasses. So it's probably
This is a trampoline.
and stuff underneath it is just
That's got out by the skin of our
I was
teeth.
reminded of this. So I just drove across North Dakota, and
out over there.
and there was this bobcat that
That
had been
sand boil?
stuck working on a frozen lake that they hadn't got out.
Oh yeah,
quite
there it is.
and the lake was beginning to thaw out the edge, and it was in the water. They tied a chain to it on a bigger rig, which was actually on the ice, which was still floating, but the ice was slowly melting at the same time, so they're going to lose the other thing as well. So I don't know if you could see this, but there might have been little mud sand volcanoes. So a typical
Sand boil?
attribute of
Oh yeah, there it is.
earthquake deposits is you get these liquefied deposits, and you get high pressures, it boils up, and it will make a conduit up to the surface. It'll just evacuate a whole bunch of water, which is what this is. You probably can't see it very well. Water that contains sand, and you get little mud volcano or sand volcanoes developing. And so all the damage in the 1989 Loma Prieta earthquake in San Francisco was mainly in the Marina District, which is all built on dredged materials, really soft, consolidated to some degree, but when it gets shaken, it collapses and it all gets held by the water, and it just becomes a slurry that has no strength to it, and buildings collapse, and septic tanks jump out of the ground because they're buoyant compared to everything around them. So that's it. So that's side investigation. So we have a bit more to talk about, so we'll look at some more things next time, and we'll